The universe is built on a secret. Every star and galaxy we see is just a tiny, glowing fraction of what is truly there. This is the central mystery of dark matter, the invisible mass that holds our cosmos together. By the end of this journey, you will understand the overwhelming evidence that forced scientists to accept a reality dominated by the unseen. How can we be sure something is there if we cannot see, touch, or light it? What clues did astronomers find hidden in the motion of stars and the bend of light itself? We will trace a century of cosmic detective work, from strange galaxy clusters to the afterglow of creation, revealing how this dark framework reshaped everything we know about space, time, and our own place in the cosmos. Are you ready to question what you think is real? The first clue to this cosmic secret was found in a city of galaxies. In the 1930s, a Swiss astronomer named Fritz Zwicky turned his attention to a dense gathering of star systems known as the Coma Cluster. This was not a lone island universe but a vast, swirling metropolis of thousands of galaxies, all bound together by gravity. To understand its stability, Zwicky applied a trusted principle from physics called the virial theorem. In simple terms, this theorem is a cosmic balancing act. It states that for a system held together by gravity, like a cluster of galaxies, the energy of motion of its members must be balanced by the gravitational pull holding them in. Think of it like a spinning carnival ride. The speed of the riders, their kinetic energy, is kept in check by the strength of the structure holding them to the ride. If the structure were too weak, the riders would fly off. Zwicky used this idea to weigh the entire Coma Cluster. He measured how fast its individual galaxies were moving relative to one another, a frantic cosmic dance. Then he calculated how much mass, how much gravitational glue, would be required to keep those speeding galaxies from simply flying apart into the void. The number he arrived at was staggering. The mass needed to explain the observed motions was hundreds of times greater than all the mass he could see from the combined light of every single star and every wisp of glowing gas in all those thousands of galaxies. The math was clear and inescapable. The cluster should have torn itself apart long ago unless it was filled with something else, something invisible providing the extra gravitational grip. Zwicky named this missing ingredient Dunkel Materie, dark matter. His conclusion was so radical, so at odds with the understanding of the cosmos at the time, that it was largely dismissed. The scientific community viewed it as an anomaly, perhaps a mistake in measurement or an incomplete theory. Yet this cluster-scale mystery, this first glaring discrepancy between what we see and what must be, planted a seed of profound doubt. If our inventory of the cosmos was so incomplete on the grandest scales, what did that mean for everything else? The evidence was about to come much closer to home, found not in distant clusters, but in the very rotation of our own galactic neighborhood. The whispers from those distant galaxy clusters would not stay silent. Decades after Zwicky's puzzling discovery, the evidence for the unseen arrived on our cosmic doorstep, hidden in the graceful spin of our closest galactic neighbors. Astronomers Vera Rubin and Kent Ford focused their attention on the majestic spiral of the Andromeda Galaxy. Their goal was straightforward: to chart the orbital speed of stars and gas clouds from the galaxy's bright core all the way out to its faint, wispy edges. According to the well-established laws of gravity, this motion should follow a predictable pattern. Picture our own solar system. Mercury, the innermost planet, zips around the Sun at a blistering pace. Neptune, far out in the cold depths, moves in a slow, stately orbit. The gravitational pull weakens with distance, so objects farther from the center of mass should move more slowly. This is what Rubin and Ford expected to see in Andromeda, but the data told a different story entirely. As they mapped the velocity of stars across the galaxy, they found the rotation curve did not fall away. It stayed flat. Stars orbiting far out in the galactic suburbs were hurtling around just as fast as those nestled near the brilliant core. This was not a minor discrepancy, it was a fundamental breakdown. The visible mass of the galaxy, all its stars and glowing gas, could not possibly generate enough gravity to hold onto these speeding outer stars. They should have been flung into intergalactic space. The only logical conclusion was that each spiral galaxy is not an island of light. It is instead the glowing heart of something vastly larger and completely dark. Every galaxy we see is embedded within an enormous, invisible sphere of matter, a halo that extends far beyond the last visible star. This halo's gravity grips the outer stars, whipping them around at the same tremendous speed. Rubin and Ford's meticulous work transformed dark matter from a curious anomaly in distant clusters into an intimate, universal truth. The flat rotation curve became the most direct and undeniable signature of the hidden cosmos, forcing science to completely reimagine the true architecture of every single galaxy in the sky. But the influence of this unseen mass extends far beyond the orbit of a single star. To witness its true power, we must pull back our view to the very largest canvas imaginable. Picture the observable universe not as a random scattering of lights, but as a single, interconnected masterpiece. Modern sky surveys, painstakingly mapping the positions of millions of galaxies, reveal an astonishing pattern. Our cosmos is structured like a vast, three-dimensional spiderweb. Brilliant knots of galaxy clusters are connected by long, delicate filaments of star systems, all weaving around incomprehensibly empty voids that stretch for hundreds of millions of light-years. This is the cosmic web, the grand architecture of everything, and like any great structure, it required a framework to build upon. Scientists can trace the origin of this web back to the faintest whispers of unevenness in the newborn universe, tiny ripples in density frozen into the fabric of space-time. Over billions of years, gravity worked on those ripples, pulling matter together. But here is the crucial puzzle. When researchers run supercomputer simulations of the universe's growth using only the ordinary matter we know, atoms and light, the result is a cosmic disappointment. The structures that form are far too smooth, too washed out. The intense radiation pressure in the early universe would have prevented ordinary matter from clumping into the rich, detailed tapestry we actually observe. For the simulation to match the breathtaking complexity of the real cosmic web, scientists must add an extra ingredient, a form of matter that feels gravity but does not interact with light. This cold, slow-moving dark matter provides the perfect gravitational scaffolding. It can begin collapsing into dense halos long before ordinary matter, creating deep gravitational wells. Then the normal atoms, the stuff of stars and planets, simply flow into these pre-existing dark matter basins, lighting up the densest knots as galaxies. The most precise maps of the universe, like those from the Sloan Digital Sky Survey, align with these dark matter-based predictions with stunning accuracy. The majestic filaments and cavernous voids are not an accident. They are the monumental, universe-spanning imprint of the invisible mass, the signature of the primary architect that sketched the blueprint for all of cosmic history. If light travels in a straight line, our view of the universe would be a flat and honest map. But space itself is curved. Einstein's revolutionary insight was that mass does not simply pull on objects, it warps the very fabric of space-time around it. Think of placing a heavy bowling ball in the center of a taut rubber sheet. Any marble rolled nearby will curve its path following the indentation. Light, traveling through the cosmos, does the same thing. It does not feel the warp, it simply follows the curve. This means a massive object like a galaxy or a cluster can act as a gravitational lens, bending and distorting the light from objects far behind it. For astronomers, this is not a theoretical curiosity. It is a precision scale for weighing the cosmos. When they train their telescopes on a massive galaxy cluster in the foreground, they sometimes see a breathtaking sight. The faint, distorted images of background galaxies stretched into long, luminous arcs, like smears of celestial paint, or even mirrored into multiple images of the same object. By measuring the precise degree of this distortion, scientists can perform a cosmic accounting. They can calculate exactly how much total mass in the foreground cluster is required to bend the light by that specific amount. The result, every single time, confirms the earlier clues. The mass needed to create these gravitational lenses is many times greater than all the stars and gas we can see glowing in the cluster. It is the most direct method we have to map gravity itself, and it consistently points to a vast reservoir of invisible matter. Perhaps the most stunning proof of this comes from a cosmic collision. Two galaxy clusters, each containing hundreds of galaxies, plowed into one another at unimaginable speed. This event, known as the bullet cluster, created a natural laboratory. In such a violent merger, the different components behave in very different ways. The hot gas, which is the normal, visible matter that fills the space between galaxies, is like a thick soup. When the clusters collided, this gas slammed together, heated up even further, and got stuck in the middle, glowing brightly in X-ray light. But the galaxies themselves and something else passed right through. By using gravitational lensing to map where the bulk of the mass in the system ended up after the crash, astronomers made an extraordinary discovery. The peak of the mass distribution, the true gravitational anchors of the clusters, did not align with the glowing gas. They were located in two clear regions far from the collision site, coinciding with the galaxies. This was a direct, observational separation of normal matter and dark matter. The dark matter, unaffected by the electromagnetic forces that caused the gas to slow and heat, simply sailed through the collision, carrying the majority of the mass with it. Here was a picture not of dark matter itself, but of its undeniable gravitational shadow. It behaved exactly as a ghostly, collisionless substance should, proving it was not just hidden, ordinary matter. It was something fundamentally different, sculpting the cosmos from the shadows and revealing itself only by the way it bends the path of light from the distant universe. The ultimate evidence for this hidden framework is not found in the present, but etched into the oldest light in existence. To peer into the universe's infancy, we must listen to its first whisper, a faint afterglow that has been traveling for over 13 billion years. This is the cosmic microwave background, the cooled remnant of the universe's fiery birth in the Big Bang. It is a nearly uniform sea of microwave radiation that fills every corner of the cosmos, a baby picture of the universe when it was just 380,000 years old. At that moment, the hot, dense plasma of particles and light finally cooled enough for atoms to form, allowing light to travel freely for the first time. That ancient light, stretched and cooled by the expansion of space, is what we detect today. But if you look closely, this afterglow is not perfectly smooth. Detailed maps from satellites like WIMPs and Planck reveal a tapestry of tiny temperature variations, minuscule hot and cold spots scattered across the sky. These fluctuations are incredibly small, just about 1 part in 100,000, but they are the most important cosmic fingerprint we possess. That subtle pattern is a frozen record of the density ripples present in the infant universe, the very seeds from which all cosmic structure would grow. The specific way these spots are arranged, their size and distribution, encodes a wealth of information about what the universe is made of, its shape, and its entire history. When cosmologists analyze this pattern, known as the power spectrum, they find it fits one model with astonishing precision. It is the lambda CDM model, which includes both dark energy and cold dark matter. The data tells us that ordinary atoms, the stuff of stars and planets, make up only about 5% of the universe's total energy budget. Dark matter, the invisible scaffolding, accounts for roughly 27%. The remaining 68% is the mysterious dark energy driving the accelerated expansion. How does this ancient light reveal dark matter? In that early, searing plasma, ordinary matter and light were tightly coupled, pushing and pulling against each other in powerful sound waves. Dark matter, however, was different because it does not interact with light. It was unaffected by this radiation pressure. It simply sat there, providing stable gravitational anchors. This difference in behavior left a clear signature in the sound waves imprinted on the cosmic microwave background. The observed pattern of hot and cold spots, the precise sizes of those spots, could only have been produced if a significant amount of this gravitating, non-interacting dark matter was present from the very beginning. The agreement between the intricate details of this cosmic snapshot and the predictions of the dark matter model is not just good, it is breathtakingly exact. This means the blueprint for our entire cosmic web, for every galaxy and cluster we see today, was already written into the fabric of the universe when it was less than 400,000 years old, dictated in large part by the silent, pervasive presence of dark matter. The universe keeps meticulous books, and its ledger reveals a profound imbalance. We call the ordinary stuff of planets, people, and stars baryonic matter, composed of familiar protons and neutrons. For decades, astronomers have conducted a grand cosmic census, trying to account for every atom in existence. They count the brilliant glow of stars in galaxies. They measure the faint X-ray hum of million-degree gas floating between galaxies in vast clusters. They even detect the ghostly fingerprints of hydrogen, the universe's most basic element, spread in diffuse clouds throughout the cosmic web. This is our inventory of the visible, yet when they compare this total to a separate, ironclad number from the universe's infancy, the books do not balance. The early universe left us two independent receipts. The pattern of the cosmic microwave background tells us how much baryonic matter existed then, and the theory of Big Bang nucleosynthesis, which perfectly predicts the cosmic abundance of light elements like hydrogen and helium, gives us the same number. Both methods agree on the total amount of ordinary matter the cosmos started with, but when we look around at the universe today, a substantial portion of those original baryons seem to be missing. They are not in stars or in the obvious hot gas. The leading theory suggests they are hiding in an almost invisible form, a warm fog of extremely diffuse gas in the vast spaces between galaxies, so thin it emits almost no light we can easily catch. Even if we eventually find all these missing atoms, the fundamental problem remains. Let us say we succeed in accounting for every single proton and neutron that has ever existed. That total baryonic mass, when placed on the cosmic scale, weighs in at only about 1/6 of the total gravitational mass we know is out there from the motion of galaxies, the bending of light, and the growth of the cosmic web. This is the definitive proof. The universe's gravity tells us there is 6 times more matter present than the sum total of all possible atoms. The cosmic budget has a staggering shortfall. No amount of searching for hidden clouds of ordinary gas or faint stars can ever fill this gap. The inescapable conclusion is that dark matter cannot be made of baryons. It cannot be planets, black holes, or cold stars made of atoms. It must be something else entirely, a new form of matter that does not participate in the complex chemistry of light, a substance fundamentally alien to the world we touch and see. This mismatch is not a minor accounting error, it is the signature of a deeper reality, forcing us to accept that the atoms we are made of are merely the rare, luminous froth on a dark and boundless sea. The universe is a puzzle we can now assemble inside a supercomputer. To test the dark matter hypothesis, scientists do not just look at the sky, they build entire cosmos from scratch. This field is known as n-body cosmology, a process of creating virtual universes governed by the precise equations of gravity. The starting point for these digital creations is the ancient blueprint we just discussed, the subtle pattern of hot and cold spots from the cosmic microwave background. These are the initial density ripples, the seeds from which everything grows. With this starting condition, researchers run the clock forward over billions of virtual years. The results are stark and revealing. When a simulation includes only the ordinary matter we know, baryons and light, the outcome is a cosmic failure. The structures that form are weak and blurry. Galaxies are too few, too small, and they lack the rich clustering and intricate filamentary web that defines our actual universe. The intense pressure from radiation in the early universe prevents the normal matter from collapsing into the dense, sharp structures we observe. But then, they add the key ingredient, cold, dark matter. In these simulations, dark matter is modeled as a vast swarm of simple, slow-moving particles that feel gravity but nothing else. They do not emit light, they do not collide with each other like atoms do. They are pure gravitational anchors, and when the simulation runs with this dark component included, something extraordinary happens. The virtual universe that evolves looks uncannily like our own. From a smooth, nearly uniform beginning, the dark matter first collapses under its own gravity, forming an intricate, invisible scaffolding of halos and filaments. Then, the ordinary baryonic gas flows into the deepest gravitational wells of this dark framework. It cools, condenses, and ignites into stars, lighting up the densest knots as galaxies. The simulation does not just produce a few random galaxies. It generates the entire cosmic web in breathtaking detail. It predicts the statistical distribution of galaxies, how they cluster together in groups and vast clusters. It matches the observed properties of galaxy halos and the large-scale emptiness of the voids. The predictive power of these simulations is not limited to a single snapshot in time. They successfully reproduce the universe's appearance across different cosmic epochs, from the first small, primordial galaxies to the majestic clusters we see today. This remarkable agreement between a purely mathematical model and the observed structure of the real cosmos, across multiple scales and throughout cosmic history, is perhaps the most comprehensive evidence we have. It demonstrates that dark matter is not merely a convenient fix for individual puzzles, like galaxy rotation or lensing. It is a coherent, robust framework that successfully models the entire story of cosmic evolution, from the first whisper of the Big Bang to the grand, glittering web we call home. The universe in the machine mirrors the universe we see, and that mirror is built upon the invisible. But what if the problem is not with the universe but with our eyes? Or rather, with the laws we thought were universal? A compelling alternative has emerged, one that does not require inventing a new form of matter, but instead questions the bedrock of physics itself. This idea is known as modified Newtonian dynamics, or MUND. Its proposition is radical yet elegant. Perhaps it suggests our understanding of gravity as described by Newton and refined by Einstein is subtly incomplete. At the extremely gentle accelerations found in the outer fringes of galaxies, where gravity's pull is incredibly faint, the rules might change. In this view, the flat rotation curves are not evidence of missing mass, but a sign that gravity behaves differently when it is this weak. Empirically, MUND has a surprising success story. With a single adjustable parameter, it can beautifully predict the rotation speeds of many individual spiral galaxies, matching the observed data without a single mention of dark matter halos. It feels like a cleaner, more economical solution, solving the mystery by tweaking the equation rather than populating the cosmos with ghosts. This is not a fringe idea. It is a serious, mathematically rigorous challenge that forces physicists to re-examine their most basic assumptions. Yet for all its elegance on the galactic scale, the universe presents a tapestry of evidence woven across different threads. When man tries to explain the full picture, it begins to fray. Take the bullet cluster, that cosmic collision. The clear separation between the visible, glowing gas and the peaks of gravitational mass, as shown by lensing, is a direct blow. Man, designed to explain motion within galaxies, struggles to account for this observation without, ironically, invoking some form of unseen matter. Then there is the grand symphony of the cosmic microwave background. The precise pattern of its temperature fluctuations, the very seeds of the cosmic web, is exquisitely tuned by the presence of both ordinary matter and a separate, non-interacting component. Reproducing that perfect cosmic fingerprint with a modified gravity theory alone has proven immensely difficult, often requiring the addition of extra components that start to look suspiciously like a dark sector. Finally, the majestic large-scale structure of the universe, the vast filaments and voids that span hundreds of millions of light-years, formed through a complex gravitational dance over billions of years. Computer simulations that rely solely on modified gravity have not yet successfully recreated the rich, detailed architecture we observe. In many attempts to make the model fit, theorists find themselves needing to add a form of matter that does not interact with light, which begins to sound very familiar. The debate between dark matter and modified gravity is not a weakness of cosmology, it is its greatest strength. It represents the scientific method in its purest form, two competing frameworks rigorously tested against the totality of evidence. Lyman stands as a brilliant testament to human ingenuity and the necessity of questioning everything. The collective weight of observations, from the bending of light in colliding clusters to the ancient whisper of the first light, continues to point toward a universe filled with something we cannot see. This ongoing challenge does not diminish the search, it sharpens it, forcing every new observation and every new theory to be more precise, more powerful, and more humble in the face of a cosmos that still holds profound secrets. The most compelling portrait of dark matter is not a picture of the substance itself, but of its ghostly shadow. The evidence comes from a cosmic crime scene, a place where two immense clusters of galaxies, each containing hundreds of individual star systems, recently collided at a staggering speed. This system, known as the bullet cluster, provides a near-perfect natural experiment. In such a violent merger, the different components of the clusters behave in dramatically different ways, revealing their true nature. The hot gas that fills the vast spaces between the galaxies is normal baryonic matter. It is made of atoms, protons, and electrons that interact strongly with light and with each other through electromagnetic forces. When these two clouds of gas slammed together, they behaved like two thick soups pouring into one another. The particles collided, creating immense friction and pressure, heating the gas to millions of degrees until it glowed brightly in X-ray light. This luminous gas, slowed and stuck in the middle of the collision, is clearly visible to our telescopes. The galaxies themselves, however, are mostly empty space. The vast distances between stars mean that when two galaxies pass through each other, the stars almost never physically collide. They are like two swarms of bees flying through one another, the individual bees rarely touching. So during the cluster collision, the galaxies, acting as these nearly collisionless swarms, simply passed right through the chaos and continued on their way, emerging on either side of the wreckage. But what of the gravity, the true mass of the system? To map that, astronomers used the universe's own scale, gravitational lensing. By meticulously measuring how the background light from distant galaxies was stretched and distorted as it passed through the bullet cluster, they could create a precise map of where the total mass, the source of the gravity, actually ended up. The result was stunning and definitive. The peaks of the mass distribution, the true gravitational anchors of the clusters, did not lie with the glowing X-ray hot gas mired in the center. Instead, they were located in two clear regions, perfectly aligned with the swarms of galaxies that had sailed through the collision. This is a direct, observational separation of components. The normal matter, the hot gas, got stuck, but the majority of the mass, revealed only by its gravity, traveled with the galaxies. This behavior is exactly what is predicted for cold, dark matter. Like the galaxies, dark matter particles would not interact electromagnetically. They would feel gravity, but they would not bump into each other or into the hot gas. They would be truly collisionless, passing through the cosmic wreck without a whisper, carrying their immense gravitational influence with them. The bullet cluster gives us a map where the light and the gravity have been pulled apart. It shows us that the missing mass is not simply hidden ordinary matter in some dim form, because that matter would have interacted and been slowed down. It is something fundamentally different, a substance that shapes the cosmos through gravity alone, leaving its unmistakable signature in the bent light of more distant suns. Orbiting our own galactic home are silent, ghostly companions. These are the dwarf spheroidal galaxies, faint smudges of light so dim they were almost overlooked. They contain only a few million ancient stars, a paltry number compared to the hundreds of billions in the Milky Way. Yet within these cosmic fossils, we find perhaps the purest signal of the dark universe. The stars in these dwarfs are not calmly drifting. Observations reveal they are in frantic, chaotic motion, zipping around in all directions at surprisingly high speeds. If gravity came only from the meager glow of their visible stars, this stellar frenzy would have torn these galaxies apart eons ago. Their very existence is a paradox, and the solution points to an overwhelming presence. These tiny galaxies are not just influenced by dark matter, they are absolutely saturated with it. Their mass-to-light ratios are staggering, often hundreds of times greater than our sun's. For every flicker of starlight, there is a mountain of invisible mass holding everything together. This makes them pristine natural laboratories. Unlike grand spiral galaxies churned by complex star formation and supernova, these quiet dwarfs are relatively simple systems. Their dynamics offer a clean readout of dark matter's gravitational influence on the smallest galactic scales. By studying how the dark matter is distributed within them, scientists can test critical theories about its fundamental nature. Is it cold, meaning its particles move slowly, allowing it to clump into these incredibly dense, small-scale halos? Or is it slightly warm, with faster-moving particles that would smooth out the cores of these tiny galaxies? The survival and internal motions of these faint satellites provide crucial constraints, helping to narrow down the identity of the elusive particle itself. In these ancient, dark-dominated relics, we are not just looking at galaxies, we are looking directly at the skeletal framework of the cosmos, revealed in its simplest, most concentrated form. Yet this elegant dark matter framework presents its own cosmic puzzles. Our most advanced simulations predict a Milky Way not just accompanied by a few dozen visible dwarf galaxies, but swarmed by thousands of small, dense dark matter clumps, subhalos orbiting silently in the vast galactic outskirts. We call this the missing satellites problem. Where are they all? The universe seems to have far fewer small, glowing galaxies than the dark matter model alone would suggest. This is not a fatal blow to the theory, but a fascinating tension, a clue that the story is more intricate than we first imagined. The answer likely lies not in the absence of dark matter, but in the complex and sometimes violent physics of star formation itself. Imagine those thousands of predicted dark matter halos as empty gravitational pots. For a galaxy to light up within one, ordinary gas must flow in, cool down, and condense into stars. But in the smallest, faintest halos, this process may be incredibly inefficient. The gravitational grip is so weak that even a single supernova explosion, the titanic death of a massive star, could blast all the remaining gas out into intergalactic space, shutting down star formation forever. Alternatively, the intense ultraviolet radiation from the first generations of stars in the early universe might have heated the cosmic gas, preventing it from ever cooling and falling into the tiniest halos to begin with. These halos would still be there, massive and dark, but utterly invisible to our telescopes, explaining why we see only a fraction of the expected satellites. This problem pushes astrophysicists to refine their models, to weave together the tale of the invisible scaffolding with the detailed, messy story of how ordinary matter ignites into light. It reminds us that dark matter sets the stage, but the luminous actors, the stars and galaxies, follow a script written in the complex language of baryonic physics. The missing satellites are not a sign of failure, but an invitation to look deeper, to understand how the dark and the light dance together across billions of years to create the universe we actually see. To illuminate the dark web, we must become cosmic surveyors, reading the shadows cast by the universe's most brilliant beacons. Far across the cosmos, quasars shine with the ferocity of a trillion suns, their light a piercing beam that travels for billions of years before reaching our telescopes. As that ancient light journeys toward us, it does not travel through empty space. It passes through the diffuse, almost invisible gas that fills the vast expanses between galaxies, the very filaments of the cosmic web. And within that gas lies a cosmic fingerprint, a spectral signature written in hydrogen. When a photon of the quasar's light happens to strike a neutral hydrogen atom at just the right energy, it is absorbed. This leaves a specific, dark line in the quasar's otherwise continuous rainbow of light, a line known as the Lyman-Alpha absorption line, but we do not see just one line. Because the light passes through countless clouds and wisps of hydrogen at different distances, each with its own redshift, we see a veritable forest of these absorption lines superimposed on the quasar's spectrum. This is the Lyman-Alpha forest, a dense thicket of dark lines, each telling the story of a specific cloud of gas the light encountered on its epic journey. This forest is not random noise, it is a detailed barcode, a one-dimensional core sample drilled through the universe along that single line of sight. By analyzing the precise spacing and depth of these thousands of absorption lines, scientists can perform a remarkable feat. They can reconstruct the density of matter, both ordinary and dark, that the light passed through. Denser regions where dark matter's gravity has pulled in more gas produce stronger, more clustered absorption lines. Emptier voids leave only faint, sparse traces. This transforms each brilliant quasar into a powerful searchlight, its beam scanning the shadowy structure of the cosmos. And we are not limited to a single beam. By collecting the spectra of thousands upon thousands of quasars from surveys like the Sloan Digital Sky Survey, astronomers can stitch together a three-dimensional map of the cosmic web's matter distribution on scales larger than any galaxy cluster. They can trace the faint, filamentary tendrils of gas and infer the massive dark matter halos that guide them. The statistical patterns found in this vast forest of lines, the way the absorption features cluster and correlate across immense distances, match with extraordinary precision the predictions of supercomputer simulations that include cold dark matter. It provides an independent, universe-scale confirmation of the matter-power spectrum predicted by our standard cosmological model. Here, we are not looking at galaxies or bending light. We are reading the subtle imprint left on ancient light as it filters through the universe's very bones, using the cosmos itself as a laboratory to trace the invisible scaffolding upon which everything is built. The Bullet Cluster was our first clear glimpse, but it is far from the only one. Across the cosmos, other titanic collisions are playing out, each offering a slightly different angle on the invisible architecture. Take a system known as MACSJ0025, a pair of massive clusters that slam together almost head-on. Like the bullet cluster, astronomers combined X-ray images to map the hot, glowing gas with gravitational lensing to map the total mass. The result was another stunning separation. The two peaks of dark matter revealed by lensing had clearly sailed ahead of the collided gas that was stuck in the middle, a perfect confirmation of the same collisionless behavior. But not every cosmic crash gives such a clean answer, and that is where the science becomes even more compelling. Another cluster, Able 520, nicknamed the train wreck cluster, initially presented a puzzle. Early observations suggested a troubling peak of mass coinciding with the hot gas in the center, a place where dark matter should not have lingered. For a moment, it seemed like a potential crack in the theory. Yet science thrives on deeper scrutiny. Follow-up studies with more advanced telescopes and refined lensing techniques revealed a more complex story. The core of Able 520 is not a simple merger but a messy, multi-cluster pile-up. The apparent alignment was likely a projection effect, with different components overlapping along our line of sight. When untangled, the data still favored a scenario where dark matter is largely detached from the ordinary matter. These varied collisions are not contradictions, they are a catalogue of natural experiments. Each merger has a unique geometry, a different impact speed and angle, putting the dark matter hypothesis through its paces under different extreme conditions. By studying this growing collection, astronomers are doing something remarkable. They are conducting particle physics on a galactic scale. They are testing whether dark matter particles might have any tiny ability to interact with each other beyond gravity, a property known as self-interaction. So far, the consistent theme from these cosmic car crashes is that dark matter is extraordinarily ghostly, showing no sign of slowing down or sticking together in these collisions. This collective evidence builds a robust case that is difficult for any modified gravity theory to explain, as such theories struggle to account for why the gravitational peaks so consistently march away from the visible matter. Every new cluster collision added to the catalogue is another data point, another piece of a puzzle that, piece by piece, is sketching the portrait of a substance that defines our universe yet remains just out of sight. This invisible framework does more than just hold galaxies together, it built them. From the very beginning, dark matter was the active architect of cosmic structure, not a passive bystander. In the aftermath of the Big Bang, the universe was a nearly smooth, hot soup of particles. But those tiny ripples in density, the ones frozen into the cosmic microwave background, held the future in their faint imprint. Dark matter, unaffected by the intense radiation pressure that buffeted ordinary atoms, felt only gravity. This was its crucial advantage. While normal matter was pushed and scattered by light, dark matter could quietly begin to clump. Over millions of years, those initial ripples amplified. Regions slightly denser in dark matter pulled in more dark matter from their surroundings through gravity, growing denser still. This gravitational instability created the first structures in the cosmos, vast, roughly spherical clouds of invisible particles known as dark matter halos. These halos were the universe's foundational molds, the gravitational wells that would shape everything to come. Only then could the story of light begin. Ordinary matter, the hydrogen and helium gas, was still far too hot and energetic to collapse on its own, but it could feel the gravitational pull of these growing dark matter halos. As the halos became more massive, their gravitational grasp strengthened, drawing in streams of primordial gas from the surrounding cosmos. This gas flowed along the filaments of the dark matter web and into the deepening wells. Once inside the halo, the gas could finally begin to cool. It radiated away its immense heat, condensing and settling into a rotating disk at the halo's center. There, under the relentless pull of gravity, pockets of gas collapsed further, igniting into the first brilliant stars. A galaxy was born. Every galaxy we see, from the smallest dwarf to the grandest spiral, exists because a dark matter halo formed first, providing the necessary gravitational anchor to gather and ignite the raw material of stars. The character of a galaxy is a direct reflection of the dark matter halo that cradles it. Think of the halo as a potter's wheel and the inflowing gas as the clay. The size and total mass of the halo determine how much gas it can attract, setting a ceiling for the eventual size and stellar mass of the galaxy. The shape and angular momentum of the dark matter halo as it spins are imprinted onto the gas. A halo with orderly, coherent rotation encourages the gas to settle into a beautiful, flat disk like our own Milky Way. A halo that is more turbulent or undergoes a violent merger might churn the gas, preventing a neat disk from forming and instead creating an elliptical galaxy, a featureless sphere of ancient stars. Even the motion of stars within a galaxy, the very data that first revealed dark matter to Vera Rubin, is governed by this relationship. The tight correlation between a galaxy's visible stellar mass and the speed of its outer stars is not a coincidence. It is a signature of the underlying dark matter halo's gravitational profile. The halo's presence dictates the rules of the orbital dance. This deep, symbiotic relationship solves enduring cosmic puzzles. It explains the stunning diversity of galaxy types, not as random accidents, but as natural outcomes from halos with different formation histories, masses, and spins. It clarifies why tiny dwarf galaxies can be so overwhelmingly dominated by dark matter. Their halos were just massive enough to trap a tiny sprinkling of gas to form a few stars, but their gravitational reach extends far beyond that faint glow. Understanding this partnership is the key to reading the life story of any galaxy, written in the interplay between the dark foundation and the luminous structure it supports. The visible universe performs its brilliant, complex ballet entirely on a stage built and shaped by the unseen. But to truly understand this invisible architect, we need to know more than just its gravity. We need to know its nature. Is it a placid, slow-moving sea or a fast, rushing river? This question is framed in a surprising way by talking about dark matter's temperature. In cosmology, temperature does not refer to heat in the traditional sense, but to the average speed of the particles in the early universe. This initial velocity is everything. It dictates how the dark matter clumps together, and therefore the very blueprint of cosmic structure. Scientists have explored three primary possibilities: cold, warm, and hot, each painting a different picture of how our universe came to be. Cold dark matter, or CDM, is the leading candidate. Imagine its particles as slow-moving, almost lethargic in the primordial cosmos. Because they are moving so slowly, gravity can easily grab hold of them, even on the tiniest scales. They begin collapsing into minute clumps almost immediately. These small clumps then merge hierarchically like cosmic snowballs, building up to form the massive halos that cradle galaxies. This bottom-up approach, building large structures from small seeds first, matches the vast majority of our observations, from the detailed cosmic web to the internal dynamics of galaxies. It is the workhorse of modern cosmology. Then there is warm dark matter. Picture particles with a bit more pep, zipping around at higher speeds in the early universe. This extra velocity acts like a smoothing iron. It washes out the very smallest density ripples. Gravity cannot hold onto these faster particles on tiny scales. The consequence is a top-down structure formation, where larger sheets and filaments form first, only later fragmenting into galaxies. This idea is intriguing because it could naturally explain the missing satellites problem, the lack of numerous small dwarf galaxies around the Milky Way. If warm dark matter suppresses small-scale clumps, then fewer of those tiny dark matter halos would form in the first place, so there would be fewer places for small galaxies to light up. However, this potential solution may create new puzzles. By delaying the collapse of the smallest structures, warm dark matter might also push back the formation of the very first galaxies in the universe. which could conflict with observations of extremely distant early galaxies seen by our most powerful telescopes. At the far end of the spectrum is hot dark matter, particles moving at speeds approaching light itself. A known particle, the neutrino, fits this description if it has mass. But if dark matter were hot, its tremendous velocity would have completely erased small-scale structure. Galaxies as we know them might never have formed. Instead, we would see a universe of vast, diffuse clouds. Observations of rich galaxy clusters and intricate cosmic filaments definitively rule this out. Hot dark matter may exist as a minor component, but it cannot be the primary architect. So where does the evidence point? The most stringent tests come from the smallest scales we can probe. The intricate patterns in the Lyman-Alpha forest, the absorption lines in quasar light, act as a cosmic microscope. They reveal the density of matter along vast distances, sensitive to clumps as small as dwarf galaxies. The data strongly prefers models where small-scale structure is abundant, aligning with cold, dark matter. Similarly, the very existence and internal motions of the faint dwarf galaxies orbiting the Milky Way suggest they are embedded in incredibly dense, small-scale dark matter halos, again favoring colder models. The current consensus leans heavily toward cold dark matter, though with a fascinating hint of nuance. The data allows for the possibility that dark matter is not utterly frigid, but perhaps slightly lukewarm, a variant that retains most of cold dark matter's successes while potentially easing some of the small-scale tensions. Pinpointing this precise thermal character is not an academic exercise. It is a direct line to the particle's identity. Is it a heavy, sluggish, weakly interacting massive particle, a WIMP born in the hot early universe, or could it be an ultralight particle like an axion with quantum wave-like properties that might exhibit warmer behavior? Each candidate particle has a predicted temperature signature. By refining our observations of the cosmic web's finest threads and the faintest galactic fossils, we are not just mapping dark matter's influence, we are taking its temperature, reading the subtle clues that will ultimately reveal what it is made of. The identity of this invisible architect remains the greatest open question in cosmology. If dark matter is a new fundamental particle, a cosmic ingredient never before seen in our laboratories, what could it possibly be? Scientists have proposed many candidates, but two stand out as the leading theoretical possibilities, each with its own compelling origin story and unique personality. The first is known as a WIMP, which stands for Weakly Interacting Massive Particle. Imagine a particle with a mass somewhere between 10 and 1,000 times heavier than a proton, yet ghostly enough to pass through the entire Earth without a single collision. Its name tells its story. It interacts via gravity and potentially the weak nuclear force, the same force behind radioactive decay, but not via the electromagnetic force that gives us light and chemistry. This makes it perfectly dark. The beauty of the WIMP is that it emerges naturally from a popular extension to the standard model of particle physics called supersymmetry. This theory proposes that every known particle has a heavier, shadowy twin. The lightest of these supersymmetric particles could be stable and abundant, a relic from the hot Big Bang that simply never decayed, making it a perfect candidate for the dark matter that suffuses the cosmos. Its proposed mass and interaction strength are not arbitrary. They are in a sweet spot known as the WIMP miracle, where the predicted leftover density from the early universe matches almost exactly the amount of dark matter we observe today. It is an elegant convergence of particle physics and cosmology that has driven decades of research. The second leading candidate comes from a completely different puzzle. To solve a deep mystery in the theory of the strong nuclear force, physicists proposed the existence of an entirely new particle, the axion. Unlike the hefty WIMP, the axion is unimaginably light, potentially billions of times lighter than an electron. It would behave less like a discrete bullet and more like a pervasive, oscillating field that fills all of space. In this view, dark matter could be a kind of cosmic background hum, a subtle vibration in the fabric of reality itself. While WIMPs and Axions lead the theoretical race, they are not the only runners. There are sterile neutrinos, heavier cousins to the known neutrinos that do not feel the weak force. There is even the possibility that dark matter is not a particle at all, but a population of primordial black holes, tiny knots of gravity formed in the first chaotic moments after the Big Bang. Each candidate paints a different picture of the early universe and predicts distinct astrophysical signatures. A universe built from WIMPs would have a specific hierarchy of small-scale structures. A cosmos filled with warm, sterile neutrinos might show a smoother distribution of the faintest galaxies. Axions, acting as a coherent field, could even produce subtle effects on the spin of stars. This diversity of possibilities means the search must be equally broad. It is a grand, multi-pronged effort spanning the globe and reaching into space. Deep underground, in abandoned mines and beneath mountains, ultra-sensitive detectors wait in profound silence, hoping to catch the rare, gentle recoil of a nucleus struck by a passing WIMP. Powerful particle colliders, like the Large Hadron Collider, attempt to create dark matter particles in high-energy collisions, looking for an imbalance in energy and momentum as the new particles escape unseen. For Axions, laboratories use strong magnetic fields to try and coax these elusive particles into transforming into detectable photons, and astronomers continuously scour the skies for indirect signals, like unexpected gamma rays from dense regions of dark matter, which could be the telltale glow of particles annihilating one another. This is the cutting edge, the transition from mapping dark matter's gravitational shadow to trying to touch the substance itself. Identifying the true particle is the ultimate goal, the key that would unlock not only the composition of the cosmos but potentially new laws of physics governing the universe's most secretive resident. Deep beneath the mountains of Italy, within a cavern of absolute stillness, a vat of liquid xenon waits in the dark. It is one of the quietest places on Earth, shielded by a kilometer of solid rock from the constant rain of cosmic particles that bombard the surface. This is the heart of the Xeno-NNT experiment, a listening post tuned not for sound, but for the most elusive signal in the universe. Its mission is audacious, to feel the gentle nudge of a dark matter particle as it passes through our planet. Think of it as trying to hear the softest possible whisper in the middle of a roaring hurricane. To have any chance, you must first silence everything else. That is why these detectors are built in deep underground laboratories, encased in layers of water and lead, their very materials purified to remove even trace amounts of natural radioactivity. At their core is a chamber filled with ultra-pure liquid xenon, cooled to -100 degrees Celsius. Xenon is chosen because it is a heavy, noble element, its large atomic nucleus offering a bigger target for a potential collision. If a theoretical WIMP, a weakly interacting massive particle, were to drift through this tank, there is an infinitesimal chance it would strike a xenon nucleus. That collision, that tiny transfer of energy, would produce two faint signatures, a quick flash of scintillation light and a puff of ionization, a handful of freed electrons. Thousands of sensitive photomultiplier tubes lining the tank stand ready to capture that dual signal, distinguishing it from the relentless background noise of mundane particles. The scale of this engineering is breathtaking. Experiments like LUX Zeppelin in South Dakota and Panda X in China operate on similar principles, each iteration larger and more sensitive than the last. They have grown from detectors holding tens of kilograms of xenon to those containing multiple tons, expanding their listening area exponentially. Yet so far, the silence persists. These exquisite instruments have not yet recorded the unambiguous ping of a dark matter particle. But in science, a non-detection is not a failure, it is a powerful result. Every year of quiet data places stricter limits on the possible properties of dark matter. It tells us that if WIMP are out there, they must be either heavier or, more likely, interact with ordinary matter even more feebly than our most optimistic models predicted. We are meticulously mapping a territory of nothing, and in doing so, we are cornering the possible. This relentless null result is gently steering the search, pushing physicists to broaden their horizons beyond the classic WIMP paradigm. The focus is shifting toward candidates that are lighter, or that interact through forces even weaker than the weak nuclear force. The quiet hunt in the dark continues, a testament to human patience and ingenuity, where every passing day of silence whispers a new constraint on the nature of the cosmos. While underground labs listen for a direct whisper, other scientists scan the heavens for an echo of cosmic violence. This approach is called indirect detection, and it operates on a thrilling premise. What if dark matter particles are their own antimatter twins? If that is the case, when two of them collide in the dense heart of a galaxy or within a dark matter halo, they could annihilate one another in a flash of pure energy. That energy would then transform, following Einstein's famous equation, into a spray of secondary particles we can actually detect. This could include a burst of gamma rays, the highest energy form of light, a shower of neutrinos, or even exotic antimatter like positrons and antiprotons raining through space. We cannot see the collision itself, but we might catch the aftermath. To hunt for these ghostly signatures, astronomers use some of the most advanced telescopes ever built. The Fermi Gamma Ray Space Telescope, orbiting Earth, continuously scans the entire sky, mapping the universe in gamma rays. Its gaze is drawn to places where dark matter should be most densely packed. The center of our own Milky Way galaxy is a prime target, thought to harbor an immense concentration of this invisible matter. Dwarf spheroidal galaxies, those faint satellites overwhelmingly dominated by dark matter, are also perfect, quiet laboratories, largely free of the confusing astrophysical noise of brighter galaxies. The search is for an anomalous spike of gamma rays at a very specific energy, a telltale line in the spectrum that would correspond to the mass of the annihilating dark matter particle. Meanwhile, closer to home, the Alpha Magnetic Spectrometer, or a MS-02, mounted on the International Space Station, performs a different kind of census. It meticulously counts the cosmic rays, the high-energy particles zipping through space. Specifically, it searches for an unexpected overabundance of positrons, the antimatter counterpart to electrons. Such an excess could be the fallout from dark matter annihilations happening throughout our galactic neighborhood. The intrigue is palpable because both Fermi and a MS-02 have indeed found curious excesses. There is an unexplained glow of gamma rays from the galactic center, and there are more high-energy positrons than standard astrophysical models easily account for. The heart of the challenge, however, is that these signals are not yet proof. The universe is a messy place, filled with natural particle accelerators that can mimic these signatures. Pulsars, the rapidly spinning corpses of massive stars, can blast out gamma rays and produce positrons in abundance. The turbulent regions around supermassive black holes can also generate similar high-energy radiation. Disentangling a potential dark matter signal from this astrophysical background is a monumental task of statistical subtraction and theoretical modeling. So far, no signal has risen to the level of conclusive discovery. Yet, the very existence of these anomalies keeps the indirect search vibrant and essential. It represents a different kind of listening, not for the gentle touch of a passing particle, but for the distant, fading shout of an annihilation that occurred perhaps millions of years ago, a silent event in the dark finally revealing itself through a ripple of light we are only now learning how to see. Meanwhile, in a circular tunnel deep beneath the border of France and Switzerland, scientists are trying to build the universe in miniature. The Large Hadron Collider is the most powerful particle accelerator ever created, a 27-kilometer ring where protons are whipped to nearly the speed of light and then steered into a head-on collision. The goal is to recreate, for a fleeting instant, the conditions that existed a fraction of a second after the Big Bang, a seething fireball of energy from which all particles, known and unknown, could emerge. This is the frontier of creation where we do not just search for dark matter, we try to summon it into existence. In these spectacular collisions, energy transforms directly into matter. Most of the debris consists of familiar particles, quarks and electrons and photons that spiral and spark through the massive detectors like ATLAS and CMS. But if dark matter particles are produced, they would tell a different story. They would be ghosts in the machine. Since they do not interact with the detector's layers of sensors, they would simply fly straight through the entire apparatus, carrying their energy and momentum away with them, leaving no track, no flash, no direct trace. So how do you find something designed to be invisible? You look for the silence, for the imbalance. Physicists meticulously reconstruct every collision event, adding up the momentum of all the particles that are seen, tracking their paths in 3 dimensions. In a perfectly balanced event, the total momentum should sum to 0. But if a significant amount of momentum is missing, if it points off to the side, transverse to the beamline, and cannot be accounted for by any known particle, that is a powerful clue. It is the signature of missing transverse momentum, a smoking gun that something unseen has escaped. Researchers sift through billions of collisions, hunting for events where known particles, like a pair of jets or a W boson, are produced alongside this mysterious, unbalanced momentum. Such a pattern could indicate that dark matter particles were created in the same collision and then vanished, stealing away a piece of the event's energy. To date, the colossal detectors have not recorded a definitive signal of this kind, but like the quiet, deep underground labs, this absence is profoundly informative. Each analysis rules out vast territories of theoretical possibility. It tells us that if dark matter connects to our familiar particles through certain forces or at certain energy scales, that connection must be even more tenuous than we thought. The collider searches are not a standalone effort, they are part of a triangulation. Direct detection experiments probe how dark matter interacts with us now as it streams through Earth. Indirect searches look for the aftermath of dark matter annihilating in space, and colliders explore the moment of its birth, testing the possible portals, the theoretical bridges that could have allowed it to be created alongside ordinary matter in the first place. By exploring this high-energy frontier, we are testing the very recipes that could have baked dark matter into the cosmic cake from the very beginning. The null result is a guide, patiently steering our imagination toward new models and lighter, more elusive candidates, reminding us that the universe's greatest secret may be hidden in the details of a collision we have yet to witness. The universe's expansion rate is not just a number, it is the heartbeat of cosmic history. Yet today, 2 different ways of listening to that heartbeat produce 2 different rhythms, a discrepancy so stubborn it has shaken modern cosmology. This is the Hubble tension. On one hand, we have the pristine early universe. By analyzing the cosmic microwave background, the afterglow of the Big Bang, we can extrapolate forward through 13.8 billion years of cosmic evolution. This method, grounded in our standard model of cosmology, gives us a precise value for how fast the universe is expanding now. On the other hand, we have the late universe. By meticulously measuring the distances and redshifts of nearby stars, supernova, and other cosmic landmarks, astronomers can measure the expansion rate directly in our own cosmic neighborhood. These two gold standard methods, one looking back to the beginning and one looking at the present day, disagree by a small but statistically significant margin. The local measurements suggest a universe expanding faster than the early universe data predicts. It is as if you calculated how fast a car should be going based on its acceleration from a stop, but when you look at the speedometer right now, it reads a higher number. Something is off in our cosmic story. This tension has led scientists to a provocative question: could dark matter hold the key? In our standard model, dark matter is simple, cold, and passive. But what if it is not? Some theorists propose that dark matter might have undergone a subtle transformation in the distant past. Perhaps a fraction of it decayed into lighter, even more elusive particles, injecting extra energy into the cosmic fabric at a critical moment and gently tweaking the expansion history. Another idea suggests an early, fleeting interaction between dark matter and dark energy, the mysterious force accelerating the expansion. Such a dynamic handshake could have altered the timeline of how the universe transitioned from being matter-dominated to being dominated by dark energy, potentially aligning the early and late expansion rates. While the most likely explanations still lie within the challenging details of astrophysical measurements, the very existence of the Hubble tension has opened a fascinating door. It forces us to consider that the dark sector, the invisible 85% of reality, might be a rich and complex world of its own, with interactions and evolutions we are only beginning to imagine. This puzzle reminds us that the universe's greatest secrets are often hidden not in what we see, but in the subtle inconsistencies between our most trusted maps of reality. The destiny of every galaxy, star, and atom is written in the balance between two invisible forces. For decades, cosmologists have framed the ultimate fate of the cosmos as a simple tug of war. On one side, the relentless pull of gravity from all matter, dark and ordinary, working to draw the universe back together. On the other, the mysterious repulsive force of dark energy driving everything apart. The winner of this contest determines the final chapter of everything. If the density of matter, particularly the dominant dark matter, were high enough, its collective gravity could eventually overcome the expansion. Imagine throwing a ball into the air with just enough force that it slows, stops, and falls back to Earth. On a cosmic scale, this would be the Big Crunch, a reversal of the Big Bang where the universe contracts into an unimaginably hot, dense state. For a time, this was a plausible, even elegant, symmetry for the cosmic story. But our most precise measurements have settled the debate, and the verdict is profound. The universe is not just expanding, that expansion is accelerating. Dark energy is the dominant player, comprising about 68% of the cosmic energy budget. Dark matter at 27% is the second most significant component, but it is not enough to win the gravitational tug of war. The data tells us the cosmos is destined for perpetual expansion, growing colder and more diffuse with each passing eon. Yet this does not make dark matter irrelevant to the future, far from it. Its precise density and behavior are like the setting of a cosmic clock. They dictate the timeline of how the universe transitions from its early, matter-dominated era to its current and future epoch of dark energy domination. A slightly denser halo of dark matter around a galaxy cluster would hold onto its member galaxies a little longer against the accelerating tide. The distribution of dark matter sculpts which structures will be the last islands of gravity in an ever-widening sea of emptiness. In the far, far future, as dark energy stretches the fabric of spacetime to extremes, the cosmic web will begin to tear. Galaxy clusters, bound by the immense gravity of their dark matter halos, will be the final holdouts, the last gravitationally connected structures in existence. Everything outside these dark matter anchors will be accelerated beyond the cosmic horizon, disappearing from view forever. So while dark matter cannot avert the fate dictated by dark energy, it writes the specific script for how that fate unfolds. It determines which stellar communities will witness the last stars flicker out together and which will be isolated in the expanding void. To understand dark matter is to read the final pages of the universe's story, to see how the invisible architecture that built everything will also define its long, quiet fade into the endless dark. The evidence for dark matter is more than a scientific conclusion. It is a mirror held up to our own perception. For the first time in history, we have been forced to accept a truth that defies our most basic human experience, that the primary substance of reality is invisible, untouchable, and forever beyond the reach of our direct senses. This is not a minor adjustment to a cosmic ledger. It is a profound philosophical upheaval. It dismantles a deeply ingrained, almost instinctual belief that what we see is all there is. We evolved to trust our eyes to navigate a world of light and shadow, of solid objects and clear boundaries. Dark matter tells us that world is an illusion, a luminous veneer on a cosmos built from something else entirely. This revelation joins a lineage of great cosmic humblings. Once we believed Earth was the motionless center of creation. The Copernican revolution displaced us from that privileged spot. Then we learned our sun was just one ordinary star among hundreds of billions in a galaxy, that itself was just one of countless islands in an expanding universe. Each step moved us further from the center. Now, dark matter completes this journey by showing us that even the stuff we are made of, the atoms of our bodies and our world, is the cosmic exception, not the rule. We are not just living on a speck in a vast universe. We are made from the rarest material in that universe. This shifts our place in the cosmic story from central actors to curious observers of a drama, largely played out on a dark stage we are only beginning to map. Culturally, this idea has resonated far beyond the pages of scientific journals. Dark matter has become a powerful metaphor in our collective imagination. In science fiction, it is the unknown fuel for impossible engines, the hidden dimension where mysteries reside, the silent force that bends the rules of reality. In art and literature, it symbolizes the unseen currents that shape our lives, the hidden motivations, the forgotten histories, the intangible forces of society and psyche that guide outcomes just as surely as gravity guides galaxies. It speaks to a universal human experience, the intuition that there is more happening beneath the surface, that the visible world is not the whole story. This cultural embrace reflects a deeper truth about science itself. The story of dark matter is not one of arrogant certainty, but of profound humility. It began with an anomaly, a discrepancy between what our theories predicted and what the universe revealed. Scientists could have dismissed those flat rotation curves or those unexpected gravitational lenses as errors. Instead, they followed the evidence into the dark. This is the essence of the scientific endeavor, the willingness to let nature tell its story, even when that story contradicts our deepest assumptions and demands we invent new chapters of physics. Dark matter stands as a monumental reminder that our models of the universe are always incomplete, temporary sketches awaiting revision. It celebrates not what we know, but our boundless capacity to ask questions, to probe the shadows, and to remain forever curious in the face of the great, beautiful unknown that surrounds us. We grasp the invisible through the stories we tell about it. Explaining dark matter requires a leap of imagination, a way to translate gravitational equations and cosmic maps into something our everyday minds can hold. This is where the power of analogy becomes essential. Think of a gusty autumn day. You stand in a forest and feel the air move against your skin, but you do not see the wind itself. What you witness are its undeniable effects, the frantic dance of leaves, the swaying of heavy branches, the ripple across a field of grass. The wind is invisible, yet its presence and power are unquestionable. Dark matter is the cosmic wind. We cannot see it, but we see its handiwork everywhere, in the whirling stars of a galaxy that should fly apart, in the bent light from distant quasars, in the grand architecture of the cosmic web. The effect proves the cause even when the cause remains hidden from our eyes. Sometimes the search itself is the story. Another common analogy describes the hunt for dark matter as looking for a black cat in a completely dark room. It is a playful way to capture the profound challenge scientists face. The room is the universe, vast and obscure. The cat is the dark matter particle, perfectly camouflaged against the void. And we are in the room without a flashlight, relying on our other senses, building exquisitely sensitive traps and listening intently for the faintest stir. Every so often, we think we hear a rustle or feel a brush against our leg, a curious signal from a gamma-ray telescope or a slight anomaly in a deep underground detector. But is it the cat or just the creak of the floorboards, the mundane background noise of the cosmos? This analogy does not trivialize the search. It honors the patience and ingenuity required, the careful process of ruling out every other possible sound in that dark room until only the truth remains. To understand a galaxy's rotation, picture a simple childhood experiment. Imagine tying a rock to the end of a rope and swinging it in a wide circle over your head. The rock is a star near the galaxy's bright center, held in a tight, fast orbit by the strong gravitational pull from the inner mass. Now, imagine trying to swing a second rock on a much longer rope farther out on your arm. To keep it circling at the same speed as the first rock, you would need to exert a tremendous, constant pull. Where is that extra force coming from? In a galaxy, the visible stars and gas at the outer edge are that second rock on a long rope. According to the gravity from the luminous core alone, they should be moving much slower, drifting in a leisurely orbit. The fact that they whip around at high speed means something unseen is pulling on them, an immense, diffuse halo of dark matter that provides the extra gravitational muscle to keep the entire system spinning as one unified disk. These analogies are not perfect scientific models, but they are vital bridges. They turn an abstract, almost philosophical concept into a tangible puzzle we can turn over in our minds, making one of the universe's deepest secrets feel a little less strange and a little more like a mystery we are all equipped to help solve. The search for the invisible is reshaping the world we can see. To listen for the faintest cosmic whispers, scientists have been forced to become master engineers, inventing technologies of almost impossible sensitivity. This relentless push for purity and precision, born from a fundamental question about the cosmos, is now rippling outward into hospitals, industries, and our digital infrastructure. Consider the heart of a dark matter detector, a vat of ultra-pure liquid xenon. Creating that xenon is an alchemical feat. It must be distilled to a level where not a single stray radioactive atom from natural decay can contaminate the chamber, a process that has driven breakthroughs in chemical purification on an industrial scale. The same is true for the other materials used, from specially formulated copper to advanced acrylics, all engineered to be quieter than any substance ever produced for commercial use. This expertise in creating ultra-clean, ultra-low background materials is not just for physics. It has direct applications in producing purer semiconductors for advanced electronics and in creating cleaner environments for manufacturing sensitive medical implants, where even microscopic contaminants can cause rejection. The detectors themselves are marvels of low-light sensing. To capture the single, faint photon flash from a potential particle interaction, physicists developed photomultiplier tubes and sensors of unprecedented sensitivity. These technologies are now finding new life in medical imaging devices, particularly in positron emission tomography, or PET, scanners. The next generation of these life-saving machines, which allow doctors to see metabolic activity inside the body to detect cancer or track brain function, relies on the same photon detection principles honed in the dark. The drive to shield these experiments has also propelled innovation. layers of ancient lead mined from sunken Roman ships because its low natural radioactivity is ideal, and complex water shielding systems have advanced our understanding of containing radiation. This knowledge directly benefits national security efforts, improving the technology used at ports and borders to scan cargo for shielded nuclear materials, making the world a safer place. Perhaps the most profound spin-off lies in the realm of computing and data. Mapping the cosmic web or simulating the evolution of a single dark matter halo requires staggering computational power. Cosmologists routinely run simulations that push the world's most powerful supercomputers to their limits, tracking the gravitational interactions of billions of virtual particles. To manage this, they have pioneered sophisticated software for parallel processing and data analysis. The techniques developed to handle this torrent of cosmic data are now being adapted to tackle equally complex problems here on Earth, from modeling global climate systems to analyzing the vast datasets of genomics and financial markets. The algorithms that find subtle patterns in the cosmic microwave background are similar to those that can find subtle patterns in medical scans or network security logs. Even the extreme cryogenics needed to cool detectors to near absolute zero are advancing the frontier of quantum computing, where maintaining such frigid, stable environments is essential for preserving the delicate quantum states of qubits. This is the beautiful, often overlooked consequence of curiosity-driven science. While the primary goal remains the profound understanding of our universe's hidden architecture, the journey itself builds new tools. It forces us to solve problems we never knew we had, to measure things we once thought were immeasurable, and to control environments with a precision that borders on the magical. The quest to touch the dark universe is, in a very real sense, illuminating new paths for human ingenuity, proving that when we reach for the stars, we also learn how to better heal, protect, and understand our own world. This great cosmic mystery belongs to everyone. While massive telescopes peer into the void and delicate detectors wait in deep silence, a parallel search unfolds on a scale no single institution could ever match. It happens on home computers, in classrooms, and through the collective curiosity of hundreds of thousands of people around the world. The quest to understand dark matter has sparked a remarkable era of public partnership, transforming passive observers into active contributors to cosmology. One of the most powerful examples began with a simple challenge. There were millions of images of galaxies from digital sky surveys, but far too few professional astronomers to look at them all. The solution was Galaxy Zoo, a project that invited anyone with an internet connection to help. Volunteers were shown an image of a galaxy and asked to classify its shape. Is it a spiral, an elliptical, or something more unusual? The response was staggering. People from all walks of life spent hours meticulously sorting through these cosmic portraits, their combined efforts creating a map of galactic structure more detailed than any algorithm could produce at the time. This was not busy work. These citizen scientists made genuine discoveries, identifying rare and peculiar galactic formations that led to new research papers. They helped trace how a galaxy's form relates to its invisible dark matter halo, turning public curiosity into published science. The model has since expanded. Other projects allow you to donate your home computer's idle processing power to run segments of massive dark matter simulations, your laptop becoming a tiny piece of a planet-spanning supercomputer. You can help sift through data, looking for subtle signals that might be missed by automated systems. This is the democratization of discovery. It builds a bridge between the esoteric world of theoretical physics and the lived experience of people who simply wonder about the night sky. When you spend an evening classifying galaxies, you are not just learning, you are participating. You develop an intuitive feel for the diversity of the cosmos, and you gain a personal stake in the answers. This engagement is amplified by planetariums and documentaries that bring the invisible universe to life with stunning visualizations, and by authors who translate complex equations into gripping narratives. Why does this public connection matter so deeply? Fundamental research, the kind that seeks answers to questions without immediate practical application, relies on a foundation of public understanding and support. It is fueled by the shared belief that exploring the unknown is a valuable human endeavor. By inviting people into the story of dark matter, scientists foster that belief. They show that this is not a distant puzzle for a select few, but a human mystery we are all unraveling together, and in doing so, they light a spark. The child who sees a dark matter documentary, the student who joins a citizen science project, the retiree who spends an hour classifying galaxies, they might just be the ones who design the next great experiment or have the flash of insight that finally reveals what the universe is truly made of. The search for the invisible is, in the end, a profoundly human collaboration. A scientific idea earns its strength not from universal acceptance, but from relentless challenge. The dark matter paradigm, for all its predictive power, is no exception. It thrives precisely because it is constantly questioned, its weaknesses scrutinized in the bright light of honest debate. Critics rightly highlight the most glaring absence. After decades of searching, we have yet to directly touch a single particle. This is not a minor footnote, it is the central unresolved tension of the entire field. Furthermore, when supercomputer simulations are tuned to match the observed universe with perfect fidelity, some adjustments feel suspiciously convenient, like fitting a key to a lock you yourself designed. On the smallest scales, puzzles persist. The core cusp problem in dwarf galaxies suggests their dark matter hearts may be smoother and less dense than the simplest cold dark matter models predict. These are not trivial issues. They are the cracks where light gets in, where new understanding can grow. Some voices in the scientific community argue that the dark matter framework has become almost too adaptable, a theoretical chameleon that can change its colors to match any new observation by tweaking a parameter here or adding a minor interaction there. A hypothesis that can explain everything, they caution, risks explaining nothing at all. This criticism is not an attack on science, it is science in its purest form. It forces proponents to move beyond comfort and into uncharted territory. It demands sharper, more falsifiable predictions. Why has direct detection remained so stubbornly silent? Could dark matter interact with itself in ways we have not considered, softening those galactic cores? Or does its answer lie in a particle so alien to our expectations that our current experiments are fundamentally blind to it? These open questions are not signs of failure, they are the very engines of progress. They are the reasons why new detectors are being dreamed up, why telescopes peer deeper into dwarf galaxies, and why theorists explore landscapes of ideas far beyond the standard WIMP. This vigorous, sometimes contentious dialogue is the heartbeat of discovery. It ensures that our map of the cosmos is not drawn in permanent ink, but in pencil, always ready for revision when a new piece of the puzzle refuses to fit. The greatest testament to dark matter's power may not be its successes, but its ability to withstand decades of such intense scrutiny and emerge not weaker, but more precisely defined, its mysteries sharper and more compelling than ever. The next great leap in this cosmic search is already taking shape, not in a single instrument, but in a new generation of eyes that will peer deeper and wider than ever before. This is the era of the Survey Observatory, where mapping the entire sky with relentless precision becomes the primary tool for decoding the dark universe. Leading this charge is the Vera Rubin Observatory in Chile. Its mission is breathtaking in scope, a 10-year campaign called the Legacy Survey of Space and Time. Night after night, its enormous mirror and giant camera will capture the southern sky, not just once, but over and over. It will catalog tens of billions of galaxies and track billions of individual stars within our own Milky Way. This relentless watch will produce the most detailed movie of the cosmos ever made. For dark matter, this data is a goldmine. By measuring the subtle, coherent distortions in the shapes of billions of distant galaxies, a technique called weak gravitational lensing, scientists will create the most precise map yet of dark matter's distribution across a third of the sky. They will see its invisible filaments in high definition and measure how its web has evolved over cosmic time. Simultaneously, by tracking exactly how galaxies cluster together in three-dimensional space, the survey will test our models of cosmic structure formation with a statistical power that is almost unimaginable today. Any tiny deviation from prediction, any unexpected pattern in the dark matter map, could be the crucial clue that points toward its true nature. Already in space, the European Space Agency's Euclid telescope has begun its own ambitious survey. Launched in 2023, Euclid is designed to measure the geometry of the dark universe. It will observe billions of galaxies out to distances of 10 billion light-years, constructing a colossal three-dimensional map. Its primary goal is to understand dark energy, but you cannot study the push of dark energy without precisely accounting for the pull of dark matter. Euclid's exquisitely sharp images will provide an independent, space-based measurement of weak lensing and galaxy clustering, free from the blurring effects of Earth's atmosphere. This dual approach, with Rubin on the ground and Euclid in space, will cross-check and reinforce our findings, building an unshakable census of the invisible mass. They will soon be joined by NASA's and Nancy Grace Roman Space Telescope. With a field of view 100 times larger than the Hubble Space Telescope, Roman will perform giant wide-area surveys at infrared wavelengths, peering through cosmic dust to see the large-scale structure of the universe with fresh eyes. It will discover thousands of new exoplanets, but its profound legacy will be in cosmology, adding another layer of depth and detail to our map of the dark matter web. Together, these observatories represent a paradigm shift. They move from studying individual anomalies or specific clusters to conducting a total, statistical audit of the cosmos. They will measure the influence of dark matter not in a handful of places, but everywhere, building a dataset so vast and precise that it will either confirm our current theories down to the finest detail or reveal the cracks that demand a revolution. On the other side of the search, the quest to detect the particle itself is scaling up dramatically. Plans are underway for the ultimate direct detection experiment, a project called Darwin. Envisioned as a multi-ton observatory of liquid xenon or argon, it would be the most sensitive listening device for dark matter ever constructed, probing territories of interaction strength and particle mass that are currently beyond our reach. Its goal is unambiguous: to either make a definitive discovery or rule out a vast remaining landscape of theoretical possibilities, cornering the particle's properties with finality. Meanwhile, the future of particle colliders is being debated on a global scale. Concepts for machines even more powerful than the Large Hadron Collider, with circumferences potentially reaching 100 kilometers, are on the drawing boards. These would push the energy frontier further, attempting to create dark matter particles under conditions that replicate the universe even closer to its first moments. Whether through the immense statistical power of sky surveys or the profound sensitivity of next-generation detectors, the path forward is clear. The coming decades will not be a quiet continuation of the search, but a decisive confrontation. These new tools are not just improvements, they are instruments of interrogation designed to force the universe to answer. They will either illuminate the dark sector at last or push our constraints to such an extreme that we are compelled to rewrite the fundamental laws of gravity and matter. Either outcome promises a discovery that will redefine our place in the cosmos, guaranteeing that the story of the invisible universe is just reaching its most exciting chapter. The invisible architect demands a conversation across every language of physics. This is not a mystery that belongs to one discipline alone. It is a cosmic riddle that sits at the crossroads of human knowledge. To solve it, astrophysicists must speak with particle physicists, cosmologists must listen to nuclear engineers, and theorists must ground their equations in the hard data from telescopes and deep underground labs. This is the true power of the dark matter quest. It forces a unification of perspective. Imagine a grand cathedral being built. The astrophysicist is the surveyor, meticulously mapping the cathedral's immense footprint and soaring arches by observing how light bends around its invisible form. They tell us where the dark matter is and how much of it shapes the cosmos. The particle physicist is the materials scientist, trying to identify the unseen bricks and mortar from which the cathedral is made. They design the delicate instruments that might, one day, feel the texture of a single brick. The cosmologist is the architect, using blueprints from the universe's first moments to understand why the cathedral took this specific shape and how it will change over eons. And the nuclear physicist is the expert in background noise, helping to distinguish the sigh of a passing dark matter particle from the constant creak of the building's ordinary materials. This collaboration is not a side effect, it is essential. The candidate particles proposed by theorists working with quantum field theory or even string theory, ideas born from mathematical elegance, must make predictions that astrophysicists can test in the motions of dwarf galaxies. The faint signals sought in vats of liquid xenon deep underground are understood only because nuclear physicists have painstakingly characterized every possible radioactive decay that could mimic them. A curious anomaly in a gamma-ray map of the galactic center sends ripples through all these communities at once, each interpreting the signal through their own unique lens. This constant cross-disciplinary dialogue means a breakthrough can come from anywhere. A new calculation in quantum gravity might suddenly explain an odd feature in the cosmic web. An unexpected result from a particle collider could redefine what astronomers should be looking for in their surveys. Dark matter, by its very elusiveness, has become a unifying force in fundamental physics. It breaks down the walls between fields that once operated in relative isolation, fostering a more holistic and more powerful approach to understanding nature's laws. The search for what is missing has shown us that the answers will only be found when we combine every tool, every perspective, and every spark of curiosity we possess. The billions spent on this search are not a gamble on a single particle, but an investment in the very act of looking. This is the ethical heart of fundamental research, a commitment to expanding human understanding for its own inherent value. To ask what the universe is made of, to trace the story from the first light to the last galaxy, is to engage with questions that have defined our species since we first looked up at the stars. Knowing that we are made of the rarest stuff in a cosmos shaped by the unseen directly addresses who we are and where we came from, providing a context for our existence that is grounded not in myth but in measurable reality. This pursuit carries a profound cultural weight, forging a shared narrative of discovery that transcends borders. The global collaborations behind telescopes like Euclid or detectors like Xeno-NNT are not just scientific partnerships, they are diplomatic achievements, uniting nations in a common, peaceful quest for knowledge. This cooperative spirit itself is a tangible benefit, building bridges of trust and communication in a world often divided. Yet history offers another compelling argument for this investment, one rooted in unexpected utility. Time and again, the quest to answer a pure, abstract question has unlocked revolutions no one could have planned. The scientists who pioneered quantum mechanics in the early 20th century were driven by a desire to understand the bizarre rules governing atoms and light. They were not trying to invent a new consumer electronics industry. Yet from their equations emerged the transistor, the laser, the entire foundation of our digital world. The intricate mathematics developed to map the curvature of spacetime for Einstein's theory of relativity later became essential for the precise satellite navigation that guides our phones and cars. The search itself forces us to invent. To listen for dark matter, we had to create materials of impossible purity and sensors of unbelievable sensitivity, technologies now finding new life in medical imaging and security systems. This pattern suggests that the greatest practical benefits often come not from targeting a specific application, but from empowering brilliant minds to solve the deepest puzzles they can find. The tools they forge along the way inevitably reshape our world. Beyond any future technology, this exploration cultivates something equally vital, a culture of critical thinking and evidence-based reasoning. It teaches a generation to question assumptions, to demand proof, and to find wonder in the complexity of nature. In a time of easy answers and misinformation, the rigorous, collaborative, and humble process of science offers a powerful model for how to seek truth. The search for dark matter, in the end, is a testament to a noble and defining human trait, the refusal to accept ignorance. It is our answer to the darkness, not with fear, but with a flashlight built from mathematics, engineering, and insatiable curiosity. To cease this search would not save resources. It would cost us something far greater: the forward momentum of our collective understanding, and the shared story that reminds us we are all participants in the same grand, cosmic mystery. The true power of this story lies not in any single discovery, but in the intricate way every thread weaves together. Each line of evidence, from the frantic dance of galaxies in distant clusters to the subtle whisper of ancient light, tells a distinct part of the same tale. Zwicky's missing mass, Rubin's flat rotation curves, the cosmic web's grand architecture, the stark separation of mass and light in colliding clusters, and the frantic motion of stars in faint dwarf galaxies, these are not separate puzzles. They are different windows into the same dark room, each offering a unique view of the singular, invisible structure within. The coherence across these vastly different scales and cosmic epochs is what transforms a hypothesis into a cornerstone of reality. It is the difference between finding a single, strange footprint and mapping an entire, hidden landscape from a dozen different vantage points, all of which align perfectly. This convergence is further cemented by the remarkable success of our digital universe. When we feed the initial conditions of the Big Bang into a supercomputer and let gravity do its work, the simulation that emerges, complete with its dark matter scaffolding, is not a rough sketch. It is a breathtakingly accurate portrait of the galaxy clusters, filaments, and voids we actually observe. The model does not just explain what we see, it predicts it. This predictive power, combined with the independent observational tapestry, creates a case of overwhelming consistency. While the fundamental particle, the true identity of this dark substance, remains the great unknown, the existence of the phenomenon itself is no longer debated in the same way. The conclusion that most of the matter in the universe is non-baryonic, collisionless, and dark is as firmly established in modern cosmology as the fact that stars are powered by nuclear fusion. We have moved from questioning if this invisible framework exists to meticulously charting its properties and grappling with its profound implications. The cosmos has been fundamentally reshaped, not by a new observation, but by the collective weight of 100 interlocking clues, all pointing silently toward the same stunning truth. Our exploration of the evidence for invisible mass reveals a universe far stranger and more magnificent than we once imagined. We have journeyed from the puzzling motions within galaxy clusters to the ancient whispers of the cosmic microwave background, from the dramatic collisions of galaxy clusters to the silent dance of dwarf galaxies. Each piece of evidence is a clue in the greatest detective story of modern science, pointing to a cosmos where the visible is but a minor component. While the fundamental particle of dark matter remains elusive, its gravitational signature is etched across the universe on every scale. This quest reshaped cosmology, teaching us humility and wonder. As we continue to search, remember that the greatest mysteries often lie in the dark. Share your thoughts on this cosmic enigma in the comments below. Subscribe for more journeys into the unknown and keep looking up and wondering what lies unseen.